You're dealing with work, money, bills, worries, friends, lovers, wait, hurry. But we got all night, 'cause I just wanna slow down. There's no one else around now, no. We just gotta slow down, yeah. There's no place to run to now on the day that we were born, 'cause I just wanna slow down. There's no one else around now, no.
So I work for proteanTecs. I think we are probably the lesser known company from the distinguished presenter before me. So I'll just spend a few minutes talking about who proteanTecs is. So we are a startup company in our growth stage, and we are located in Haifa, Israel. Our goal is to provide a uniform language that breaks the siloed approach of different stages in chip design and manufacturing and testing processes. We call that UCT, Universal Chip Telemetry. And today we are going to focus about chip telemetry and data, deep data analysis designed for the quality and reliability monitoring of heterogeneous packaging. So I'll use that slide from TSMC just to explain some of the challenges we are seeing in this type of application. So two type of packaging technologies offered by TSMC. CoWoS is based on silicon interposer, while Info is based on organic substrate. There are some unique challenges and there are common challenges between those two type of packaging technologies. Silicon interposer is characterized with a very high density, I would say ultra high density, a very high speeds, and it is using micro bumps, and we see that the micro bumps are probably the weakest point in the link between die-to-die connectivity. On organic substrate, the focus is on ultra high speeds, still very high density, but even more on high speeds. And in a hybrid bonding type of packaging, the weak link will be actually the trace itself, because we may not have micro bumps at all. But what's common is that those type of links are lacking redundancy. So maybe there is a redundancy at the system layer, maybe there are spare lanes, but there is no physical redundancy. There is usually just one micro bump, and of course there is only one trace between two sides of the links. The other challenge that we see is limited visibility after assembly. So you may be able to probe and trace the device itself and the substrate before you assemble. But once the system is assembled, you are lacking visibility. The other thing that is a challenge, and we all know that, is that chips degrade over time. So they may be born fully functional and performing as expected, but over time they will degrade. And the question is, how do you track and monitor this degradation and know when your chip is coming to the end of its life? We are seeing those packaging challenges at every stage. So during new product introduction, we would like to characterize every single pin. We are talking about thousands or tens of thousands of different pins. But because we cannot go and probe each of those signals or these pins, it's very difficult to do characterization. So we may do characterization by groups. For that, we would not like to have some guard bands, but because of this application is already stressing to the limit, we have very limited room for a guard banding. In volume production, again, we know there will be outliers, there will be a parametric shift and systematic shift, but we have very low visibility in quality screening. And even if we could, the vast connectivity leads to a tremendous amount of volumes of data coming from each chip and from the amounts of chips that we manufacture. And we have to keep in mind that scrapping assembled product is very expensive. So we would like to know if we are assembling a defective device or a device that is already below the standard average before it is a final product. During in-field, we'd like to know if there is performance degradation over time. We would like to have some alerting mechanism because the cost of having a system down in mission critical application is very high. So we all know the amount of data transferred in data centers, in communication channels. Those systems cannot be going down, and we have to, if we need to take a system down for maintenance, it has a very high cost. So our solution is based on two pillars. The first pillar is agents. Agents are tiny digital sensors that goes inside the chip. So we actually provide silicon IP to the silicon design company. They put those sensors inside the chip, and then we call them agents. Agents because they provide information that can be used later during deep data analytics. The second aspect of our solution is the data analytics software. It's a platform software that can take the telemetry information coming from the chip at every single point in time, process it using machine learning algorithms, and provides insight and actionable items that you can use to make decisions about the health of your system. So Proteus is the name of our data analytics platform. From the left, you can see it will receive signal measurement and margin measurement. It will run application, it will run algorithm and machine learning, and will provide the insights. The insights will be like performance measurement per pin, will tell you about your signal integrity, your drive strength of your drivers, the lane integrity, and the microbumps integrity. What is very different in our approach than BKMs is that BKMs usually use logic-based algorithms to test the link after it is assembled. We're talking about power-on devices during wafer sort or final test, but because we are talking about heterogeneous packaging, it must be a fully assembled system. It's the first time that you can power on your device and check the entire lane. So logic-based is the function that is commonly used. It will give you a pass-fail indication. But we are taking it to the next level because we will do actually a full lane grading. We will tell you not only if the lane is passing or failing, we'll also let you know what's the performance of this lane. How the parameters of this lane are within the specification limit. I will now go and talk about two types of agents that we are offering today. One is optimized for tile connectivity or D2D, die to die, and the second one will be focusing on HBM. In tile connectivity agent, we are talking about devices that can be assembled either on a silicon interposer or organic substrate. And I explained before that the challenges, some of them are unique and some of them are common. So I will just briefly go over those challenges again. On silicon interposer, we are focusing on the microbump. We have single microbump and we have to know what's the performance of this microbump. And quality issues may be related to cracks on the microbump or some assembly defects. On organic substrate, again, we are lacking redundancy, focusing on the trace itself. And the quality issues can be related to either open or shorts, or to even bridge shorts of signal to signal or signal to supply. I will remind everyone that the cost of risk escapes is very high, and that every interconnect quality issue may lead to a full system failure. So the agent we are offering will sit on both sides of the link. So it will be embedded into the PHY, and two dies assembled on the same substrate will be able to communicate each other. And while the communication is running, those agents will monitor continuously the signals and the timing of the signal. So what we are doing, we're actually tracking the signal timing at the receiver and reporting the margin of fail. The margin is in terms of timing. And we will do that on every single lane, and we'll do that without affecting the timing of the signal itself and without any significant power penalty. And again, it will allow us to measure per pin margin versus the sampling clock that can be rising or both rising and falling if it's a DDR approach. This is an example of how it operates in real life. So on the left, you can see a package using 3 dies, and die 1 is connected with a D2D interface to die 2 and die 3. And let's say that there is some resistive short between 2 adjacent signals or traces on that substrate. So on the right side, you will see how it will be showed on our platform. So the data, the analytic data from the agent will be uploaded into our data analytics software, and it will be processed, and statistics are shown. And you can see on the right side that in group D, one of the pins is showing a lower than expected timing margin. It is maybe even within the specification, but it is flagged as an outlier. And then the user can take decision whether to continue and monitor this pin until it is reaching the specified timing margin, or can take preventive action and actually switch this pin into a spare lane. HBM monitoring is very similar, but it is dedicated to HBM systems. The main difference in HBM monitoring is, first of all, we are now focusing on the microbump. We know that on an HBM system, while the ASIC is connected to the interposer, usually with multiple microbumps, but because of the high density of the HBM connectivity, there is only single microbump connecting the PHY and the DRAM stack. Our solution for HBM is actually based on a single side observation. Our agent is only placed inside the PHY. Still, we are able to measure a degradation of both the near-end microbump, the microbump connected to our device under test, as well as the far-end microbump, which is actually part of the logic die controlling the HBM DRAMs. So on this slide, you can actually see how we do that. We have an agent integrated into the customer's PHY. This agent continuously monitoring a transmitted and received signal, and by doing that, we can measure and track and report near-end microbumps performance and far-end microbumps performance. By the way, we are not only looking at the microbumps, we can actually track changes in the behavior of the drivers and transmitters on both ends of the link. So actually for HBM, what we do is something similar to an embedded virtual scope. We actually measure the slew rate and amplitude of the signals themselves during mission mode, and we can reconstruct the signal at the pin, how it looks like from our side of the link. And by doing that, we can determine the quality and performance of the link. We are very fortunate to have GUC as an early adopter of our technology, and GUC is one of the products is a line of HBM PHYs in 7 nanometer and 5 nanometer processes. They have adopted our monitoring and analytics solution in their product line. and they allow us to report results taken from their early test chip of HBM in both 7 nanometer and 5 nanometer devices. So this is in fact measurements done by GUC that explains how you can actually use the information to understand if you have a problem or some degradation effect on your package device. So on the right side, you can see how a far-end microbump degradation will look like. So over time, the resistance of the microbump will increase, and we will see that the slew rate of the device and the amplitude on the receive side will be degraded. By that, we'll know and predict when this microbump is going to fail. On the left side, you're seeing a near-end microbump failure or degradation, and actually the phenomenon is different. So if the resistance of the near-end microbump increases, what it does is that it reduces the effective capacitance seen by the driver, and therefore the slew rate will actually increase as the quality of the microbump decreases. And again, those are real measurements taken on HBM2E 3.2 gigabit per second test chip by GUC. This is another view, again, used on the same test chip. So we have loaded all the measurements of all the pins from one specific device, and we put them into groups, and we compare those each group to pre-silicon information and during measurement in different type of tests, and we can highlight specific pins that behave different than their groups in the nearby family. So you can see on the left side 2 pins that one in each group that have been outside the average test and close to the limit of the specification, but still within the specification. So in a logic BIS type of measurement, this will be flagged as okay, but we tell you already that these pins are close to their specific specification limit, and you have to consider taking a proactive action. On the right side, you can see measurement of amplitude of the signal, and again, you can see one pin whose amplitude is very close to the specification limit. What this technique helps us or allow us to do is to do in-field degradation monitoring. So I would like to emphasize that those measurements we are doing are taken while the chip is running in mission mode in normal life. It is not running in special BIS mode. You don't need to put it on test mode, and it doesn't need to be on a tester itself. It can actually be while the chip is assembled in system running real application. We continuously take this information, extract it from the chip, and load it to our data analytics platform and provide this visibility. So you can see here, for example, data being fed from one specific chip, and over time the degradation caused the measurements to degrade until they reach a degradation threshold. This threshold is set up higher than when the system will actually fail. So you will get an alert before the system actually fails, allowing you to take a decision, for example, to do predictive maintenance, to take down a system, to run a software and use a spare lane, or actually decide to replace a module in your system. All this can be done in mission mode. To summarize, Proteus in action is a full comprehensive solution designed for both die-to-die and HBM type of interfaces for every single multi-die packaging technology. It will help you to monitor the quality of your device through its lifetime, from new product introduction to high volume production, system production, and in-field operation from the chip birth and until the chip death. And every single part of the way, you'll get alerts about quality escapes of your chip. I would like to use my remaining time to say that while we talk today about our tile connectivity agent and HBM agent, we actually provide comprehensive analytics solution to measure and report information from taken directly from your device in many different aspects. So we are not only talking about the high-speed interfaces, we can actually continuously monitoring the transistor characteristics and performance, design performance, your power performance, as well as clock. And all this information is then loaded into our data analytics platform. And Proteus is our data analytics solution that will bring everything into a single dashboard and provide you a full visibility into the health of your real-life system.
Imagine a world where the possibilities are endless, where everyone can participate and everyone can prosper. A world where how we live, how we learn, how we work, and how we play are all transforming. This is the world we live in now. There are already 30 billion connected devices and 200 million plus connected devices each new day. It's a world where every part of our lives is advancing faster than ever before. With 1 trillion connections by 2030, half of the world's population is on the web, where cities are becoming the centers of learning, culture, careers, and rising economies that enhance our lives. At the speed of digital, innovation is transforming our planet. From smart factories to space exploration, from virtual medicine to energy alternatives and sustainable farming, from cutting-edge medical science to the world's most advanced semiconductors, we are redefining technology to make our world a better place. Led by networked intelligence, social media, mobility, AI, IoT, and big data, we have entered the 4th industrial revolution, and it is disrupting every industry, every country, and every life for the better. At SEMI, we serve this incredible ecosystem that helps make the digital world possible. That's why our new story is so much bigger, because SEMI is more. Today, we're extending our reach from semiconductor design to equipment, materials, devices, and applications. We're driving value in workforce development, expos, standards, and R&D funded programs. We're providing insights and exploring new opportunities with thought leadership. We're inspiring innovation and industry engagement through our technology communities and partnerships. We hold the big conversations that drive growth, influence public policy, and help make technologies safer. And together, we fuel endless possibility. SEMI. Together, we are reshaping tomorrow.